Okay. Good afternoon, everyone. So I hope you are safe and healthy, and also even it is afternoon in Indonesia, and also I hope you're not sleepy. So because we will have a very interesting lecture from Professor Akbar Rhamdhani. So Professor Akbar Rhamdhani is here with us now. He's professor in Swinburne University, a colleague of Professor Jeff Brooks, and both of them were my supervisors, yeah, during my PhD study. Okay, so and he graduated from ITB, from ITB, yeah, in Teknik Material, and he had PhD from McMaster University, Canada. Okay, looks like this is 1 o'clock already, so I would like you to listen to the guest lecture, and I hope you can get more interesting topics, yeah, because after this, the students need to have a group group paper assignment about interesting topics about process metallurgy, anything, maybe urban ores as well. So I hope this can be a great source to learn as well. Okay, Professor Akbar, time is yours. Yeah, about 2 hours, yeah, with the question and answers.
Okay, thank you very much, Dr. Winnie Wulandari. It is nice to basically catch up with you again. It's been a while. And
okay, before this, you can open your video first, so at least we know that there's a guest lecture here. Okay, silakan buka dulu videonya sebelum dimulai. Atau mungkin susah. Okay.
yeah, so you want me to continue?
Yeah.
Yeah. So yeah, it's a pleasure for me to join you all today. It's 1 o'clock in Indonesia, but it's in the afternoon here in Australia. So of course it's always nice to talk with students, especially from your old sort of university. So I hope you will enjoy this lecture. So I'm going to talk about urban ores. Yeah. So I'll explain along the way what is it, and in a way, I think you already get some ideas from the previous lectures. This is sort of related to that, but we'll be focusing more on an aspect that relate with rare earth elements. Yeah. So right. So let me just share my screen. Okay. Let's see. Now. Okay. So this looks okay, Winnie. I think it looks okay. Yeah. Everybody can see the presentation. Good. Okay. So basically, what I'm going to talk about is urban ore processing, particularly focusing on processing of of ores that contain rare earth elements, including processing of products and of live products that contain rare earth elements. In particular, REPM, which stands for rare earth permanent magnet. So now, before I go further, I just want to explain a bit here. Well, my expertise is in extractive metallurgy, right? And in the past couple of years, 5 to 7 years, I've been focusing my research in applying my expertise in supporting resource efficiency and circular economy. So my current research lies around processing of alternative sources such as urban ores, great ores, extraterrestrial resources, ranging from developing new processes to refine and extract metals from these resources, yeah. Removing impurities and production of ultra pure materials. Yeah. And the other thing that has been my focus is we want to do this with as low as possible in terms of low carbon footprint. So the fact that we're using, for example, renewable energy sources such as solar energy, that is part of that sort of effort. Yeah. So if you look at on the right-hand side there, it's showing us a traditional route of production of a product, mining, yeah. And you take the minerals, the ores, yeah, and then you process them, you extract the metal to produce metals, and you design a product and you manufacture these metals into those products, and we use these products. And at the end, of course, after the product actually, at the end of their life, we process this product using, go back in the loop. It can go back to the mineral processing, can go back to metal production, or directly remanufacture it. Yeah. So as you can see from here, it's sort of circular. So this is one of the basis of circular economy, right? Now, a more detailed sort of expanded view of this can be seen in this picture here, right? So in essence, in here, the focus actually not in the original ore, but more on the non-traditional ore, which we call urban ore. Yeah. So urban ore is anything above the ground. Yeah. And when we process this, we call it urban mining or urban ore processing. So for example, here, after we use the products and and they're at the end of their life, we can put in these end of life products into the metallurgical sort of processing circuit here. For example, here, after the use, you actually use the same similar process that we use for processing traditional ore. You collect them, you dismantle, shredding, and you use physical separation, right, to separate the particular component or elements or fraction, yeah, and then you process them using different metallurgical processes, right? So in here, the knowledge of process metallurgy will play an important role, right? So so that's the thing that I want to mention from this sort of slide. So one of the key drivers or enabler for circular economy is metallurgy, process metallurgy, or extractive metallurgy. So learning in this unit, it is actually good. You can later on, participate or growth base. Another thing that I want to mention is, because I teach thermodynamics, yeah, I also want to mention in all of this, the understanding of thermodynamics is vital. Yeah. So, and as you also understand, when you're learning about process metallurgy, thermodynamics is one of the key aspects that provide the basis for understanding the process, the development of process, and that kind of activities. Yeah. Now, so all of these products, different products, I think if learned about that a bit in the previous lectures. There are many of them. It can be anything. Right? It can be, you know, an example in there, lamp, yeah, fluorescence lamp. It can be, you know, waste PCB. It can be, you know, rare earth permanent magnet. It can be anything. These actually are resources. Yeah, so we need to be able to process this one. And unfortunately, different types of products will have a different composition, will have a different chemistry, and that will govern the processing route that we take to process this one or to recover these elements. Yeah. So you know, so it's worth noting here that the consumer products are quite complex, and we will need to consider this complexity when we want to process the this product. Right. So you learn a bit about e-waste. I just want to also touch base on this one because I want to mention in particularly about e-waste in Indonesia. Yeah. So e-waste is one type of urban ores. It's defined loosely as anything, you know, from, you know, fridge, from TV, from PC, cell phone, batteries, PV cells, sometimes considered as a e-waste as well, and other sort of electronics component, right? So when we talk about e-waste, we have to be careful. We need to sometimes specify what you mean by e-waste. Yeah. So as you probably aware, we have growing you know, problems in terms of generations of these types of waste, yeah, electronic waste. So we have about 50 million tons generated annually globally, yeah, and there are challenges and also opportunities coming with this one. Of course, there are you know, precious elements that can give us the economic value, yeah. But there are also other elements that quite hazardous, and there are elements that difficult to recover, and so on. Yeah. So in particularly in Indonesia, so we just did some study. You know, it's submitted to a paper, and it's still under a reviewing process, and hopefully it will be published soon. But this is what I want to point out, and this is in relation to Indonesia. This is where you, as a student, can see the potential in Indonesia, and hope that you will want to contribute to this solution in the near future, right? So basically, we predicted that the e-waste generation in Indonesia, right, in 2020 is about 2 million tons. So the amount is actually pretty high, right? 2 million tons. And even this estimation is a safe estimation, is under predicting. Yeah. So in actual could be more than this because of you know, the informal sort of circulation of electronics. Because we calculated, we determined this one based on a direct import and export data, and expand from there. So as you can see from here, in 2020, roughly we got a 2 million tons e-waste generated, and we predicted that at 2040 that can go up to 3.2 million tons, yeah, annually generated. And some of this every year actually process is very low, less than 5% actually processed. If we do not increase the recycling rate there, of course, we will end up with a large amount of e-waste by 2040. Now, if you try to quantify the economic value of this e-waste just based on selected elements. such as copper, silver, gold, platinum, and palladium, you can actually calculate by 2040, right? There is a potential economic value of about 14 billion amount of wealth. Yeah. So it is important for Indonesia to be able to process this within Indonesia, not just sending the e-waste elsewhere. So, and to be able to process this one in Indonesia is quite crucial. And that is the role in the near future that you can play to help solve this this problem, but also challenge opportunities. Yeah. Now, in terms of the breakdown of the e-waste, right? So in here in Indonesia in 2020, the majority is in the form of small equipment. Yeah. That includes cell phones, yeah, and other small sort of gadget, right? And the rest basically, ranging from screens, other small IT equipment, lamps, and temperature exchange. That's basically just a heat exchanger and that kind of applications. And also we can see from the right-hand side there, the distribution of the e-waste around the major island in Indonesia. Now, obviously, the most e-waste generator is the island of Java. This reflects the population of Java itself in the relation with respect to the other island in Indonesia. So we predicted that about 56% of e-waste this is in 2020, generated in Java Island, and that we can calculate what that is. So based on this data, we also sort of try to develop a map of distribution across India, and this is the result, and is around Java and also Sumatra. So this one also break down in terms of not just island but also province. Yeah. So this for different provinces in Indonesia. So you can see from here there are also areas where we don't have much e-waste generated. In light colors there, such as in Sulawesi, the small island there. So I'm not good in Indonesian geography, but anyway, so you can see from here where the concentration of e-waste generated, and I don't have it in here, but in the paper, which hopefully going to be published soon, we also have the different metallurgical facilities that spread around Indonesia, where you can sort of try to connect it with this e-waste distribution to try to come up with some recycling system. Okay? So so watch this paper. Once it comes, you can look at how we sort of propose the recycling system for Indonesia, where we connect this e-waste distribution with the major smelter around Indonesia, and how we process that. Right, so now let's focus in more detail. So we're going to try to focus more on one type of e-waste, yeah, and that type of e-waste is uh, basically rare earth permanent magnet. Yeah. And these content or the materials that I'm presenting in here mainly coming from these references. Yeah. So we had one PhD student recently, Muhammad Firdaus, who actually also of Indonesia origin, looking at processing of rare earth permanent magnets with a focus of high temperature processing. Yeah, in particular, understanding the oxidation mechanisms. Another student who's continuing the study, looking at the oxidation of the end of life rare earth permanent magnets. So and we have also published a paper that outline different types of processes to recycle the magnet waste that focus using high temperature processing. Yeah. Okay. Now, before we go into details about recycling of the magnet itself, I thought I should start with a few steps back, yeah, to try to first of all looking at the elements that involve in this magnet, yeah, and so we call this element rare earth elements, REE. So in a sense, we have about 17 elements that categorize as REE, and that mainly elements in the period 6 in the periodic table, plus some elements such as scandium, yttrium, and lanthanum. Yeah. So these are, red boxes there covering the different elements. So those are the rare earth elements. Scandium, yttrium, lanthanum, cerium, praseodymium, neodymium. Now PM, I don't remember what's PM. Samarium, europium, gadolinium, terbium, dysprosium. I don't remember how. I don't remember air. Terbium and lutetium. Yeah. Now, people usually classify these elements into two categories: light and heavy. Yeah. So light consists of elements from lanthanum to europium, sometimes from lanthanum to samarium, and the heavy one is from GD, gadolinium, to lutetium, but also including the yttrium as well. Yeah. Now, some people added a middle classification called middle REE. Usually just focus on samarium until dysprosium. But the common sort of classification is the light and the heavy REE. Now, the main difference in here is of this classification coming from the electron configuration as well as the coordination number. So for the light REE, have a coordination number between 8 to 10, where the small, where the high, the heavy REE have a smaller coordination number, which is 6 from 8 there. Yeah. So these are the elements of interest, right? So why? Because basically these elements are good for the application of magnetic application, right? So the most common elements used for the magnet application is neodymium, praseodymium, and dysprosium. But there's also samarium, right? And the figure on the left there showing us the different magnet application. Previously, we focus on using steel magnet, and alnico, ferrite, and then most recently, the permanent magnet actually based on rare earth of rare element of samarium. So different types of samarium alloy, SmCO5, SM2Fe 17 and 3, SM2CO17, and since 1990s, the NdFeB and their sort of alloy, yeah, is the one that is commonly used for this magnetic application. Now, of course, the magnetic application itself in the actual daily application can be in various sort of applications, such as in electric vehicles, hard drives, yeah, generators, waveguides, yeah, electric bikes, electric storage, and magnetic brakes. So in a sense, magnet, everything that using magnet, and also the use of these elements, making it make us able to make magnet, strong magnet, um, that has small size. So small applications, such as in hard drive, for example, mobile phone, greatly, you know, um, enabled by the invention of this magnet base from rare earth elements. Right. Now let's look at how we actually, well, first of all, how these elements are present in nature, right? So unfortunately, we don't have quite a major rock forming for these types of ores that contain rare earth, right? We actually find this REE in as part of other minerals in form of residual fluids, and also processed after particular process, such as when you have a heavy minerals such as ilmenite, rutile, and zircon, and you process it, and you have a rare earth bearing minerals in there. Yeah. So so that's why we call it rare. Yeah. So it's rare. It's not really rare in terms of the amount, but it's more like rare in terms of it's difficult to find rock that mainly contain just this rare earth elements. So it's more of spread or embedded in other minerals. The reason is well, because it's also quite a large atoms, these elements. So it cannot fit to the major mineral such as silica, right? So it's much bigger than silica, so it cannot be embedded in there, and other common minerals. So the typical rare earth minerals that we use to get REE, basically there are three of them: bastnasite. So this mainly a fluorocarbonate type of minerals. Yeah. So you can see the picture there on the left hand side and the corner there, which contains ceria, lanthanum, yttria, and other types of elements. Second, monazite, which is a phosphate type minerals, right? So these two are the main minerals that used to get the rare earth element, the main source. But there's a small amount of minerals called xenotime, which usually associated with monazite as well. Typically, if this is a phosphate types of ore. Yeah. So the table on the top there, on the top right there, showing us the typical compositions of the rare earth ores. Yeah. So mainly bastnasite. You've got sodium oxide, about 50%. So that's the main, constituent there. You've got a large amount of lanthanum oxide and neodymium oxide, right, and praseodymium. And the rest is just small amount there and trace elements as well. And in monazite, also similar. You've got the sodium oxide, lanthanum oxide, and neodymium oxide as the main sort of component. And yeah, so the rest is just a small amount there. Now, I should also mention, usually many of these rare earth elements found in the same sort of same ores, yeah, as you can see in here. So they can form quite a nice solid solution in the ores. Right. So what I'm going to explain briefly in the next few slides is how we first process these ores. Yeah. And because later on you will see how some of these processes, yeah, use as well for processing of the magnet waste, yeah, or magnet end-of-life magnets as well. Okay, so if we were to process the REE ores, right, the most common routes use actually a hydrometallurgical route. Yeah. So as you know from this course, hydrometallurgy route, there are many of them, which in a sense are trying to use chemicals to leach out particular elements and precipitate those elements into the and then we get the elements there. Now, so the process quite similar to when you process other ores using hydrometallurgical route. First, you want to do a beneficiation process, yeah, trying to remove as many gain materials or any unwanted materials as possible. So there are a number of processes that you can do, ranging from gravity concentration, separating these ores based on the density, in a sense, magnetic separation based on the magnet property, magnetic property, high tension separation, and other stuff. In some process, we also use also flotation to enhance this beneficiation process. Yeah? So in a sense, to enrich the mineral content of the ore. After we do that, we then do the followed by precipitation or solvent extraction. So the one that we have here on the right is an example of processing bastnasite REE ores. Yeah, and in here, first we have bastnasite pre-concentrate. So we do the physical the beneficiation and flotation process first, and then we use a leaching process to get a leach liquor that contain thorium, iron, aluminum, calcium, in addition to the rare earth elements. And then we precipitate the rare earth elements using the different precipitation sort of solution there. So for example, here, the leaching itself, we can use sulfuric acid or hydrochloric acid. And in some sort of process, they also do a sodium hydroxide treatment to enhance the separation. And after leaching, the precipitation process, we form red earth oxalate or sodium red earth sulfates, basically using different types of cation exchanger, such as B2EHPA or P2O4. We can also use P5O7, or Cyanex 923, and other sort of cation exchanger. So this one is an example of monazite processing to form different types of, or to precipitate or extract different types of rare earth oxides. Yeah. So this is an example of Rhone-Poulenc process. Yeah, to process monazite. So first you add sodium hydroxide, basically a digestion process, and to form rare earth hydroxide in here. And you can then leach using nitric acid or hydrochloric acid, right, to separate different types of elements. And from here, you can have a mix, chlorides, fluorides, right? So we call that mix or mixed metal. So in the end, we have a mix. We have a mix rare earth elements at the end, or you can also separate into different types of oxide there. So you can see the process flow sheet is quite complex, using different types of solvent extraction technique there. This one also, this one is for Cenotyme. This is a flow sheet for production of yttrium oxide. First, you leach it using sulfuric acid, form rare earth element sulfate, yeah, and use D2EHPA for the solvent extraction. At different stages here, you can extract different solution of rare earth elements. So once we get that rare earth elements, usually in terms of chlorides, fluoride, and oxide, we can then further process to make into the alloys. Yeah. So there are different types of process that we can choose. We can take metallothermic reduction, for example. Usually we use that one for fluoride and chloride. So the reaction on the right there, showing the general metallothermic reaction. So RAN plus IM equal to R plus IMA N over I. So in essence, you have rare earth chlorides or rare earth fluoride, and then you react that with a metals, yeah, or reductant. In this case, can be calcium, lithium, and so on. And basically, the calcium will tie the chlorides and the fluoride, and you'll end up with these rare earth elements. Yeah. So an example for the chloride and fluoride shown at the bottom there, RCl3 plus lithium, producing the rare earth plus lithium chloride. Second one is RF3 plus calcium, producing the rare earth plus CaF2. So that's the reduction. So in reduction, you can use hydrogen, for example, as well as metallothermic, right? So when we look at this one, the basis is actually the thermodynamics. So we will need to understand in more details about how these compounds, chlorides, fluorides of different rare earth, uh, stable compared to these other elements. Yeah. Now, before we go into that in more details, I just want to also mention here, you can also use molten salt electrolysis, right? So in essence, you dissolve this fluoride or chloride or oxide in fluoride or chloride salt, right? And you use electrometallurgy. So you apply current or voltage across in this bath, and you basically deposit or precipitate the elements based on the composition voltage of each of that particular element. Yeah. So we also going to look at that in more detail in the next few slides. So we in here it's a summary of those processes and the characteristic included in there, and the typical metal that we usually apply, or we usually apply the particular method to get that particular metal, and so on. Right. So this is what I was talking about earlier. So the picture on the left is the standard free energy information of different types of rare earth oxide as a function of temperature, right? So this, in a sense, is like it's basically Ellingham diagram for oxide. Yeah? If you remember, so you can see from here that these different rare earth oxide have a similar value of delta G formation, right? In particularly in the one on the middle there. So that's why it's very difficult to separate, some of them. For example, in here, separate lanthanum with samarium, lanthanum with neodymium, or with gadolinium, because they all sort of similar delta G there, right? And so on. Now, I don't have it in here on this particular graph, but if you look at this one and try to compare with the common oxide, this actually sits quite low at the bottom. So it is actually sits at the bottom with calcium oxide, with magnesium oxide, with titanium oxide, with aluminum oxide. So in fact, it is mainly only CaO, calcium oxide, that lies under this rare earth element sort of lines, right? So basically, that's why we use calcium as a metal reductant, metal reductant for these rare earth elements, right? So this also quite important because the fact that Re oxide sits at the bottom, when you try to process these elements using pyrometallurgical route, right? Mainly they will end up in the slag because they are pretty stable, and they lies with the magnesia, alumina, silica, and also calcium at the bottom there. So another thing that for you to understand in here is that consider, I'm sorry, that's going back. Considering this graph, you also can appreciate that when you have a slag, such as steel making slag, for example, or slag from blast furnace, even slag from copper making slag, right? Which is very calcium silica slag, right? And then you process these rare elements in the circuits of iron making, steel making, and copper making. They will end up in the slag, right? And if you reduce them, you won't reduce and get this rare earth oxide, right? You'll get the less stable oxide, such as iron and so on. And you'll end up, so basically it's difficult for you to use a direct reduction of slag. So you have to either dissolve it in salt, yeah, that's the salt electrolysis process, or you form it in you form into other compounds such as fluorides and chlorides before you reduce them. Anyway, so the one on the right is the stability or the standard free energy formation of different types of rare earth chlorides as a function of temperature. Similarly, in terms of the delta G, they all similar or lie close with each other, right? And so on. I also have a graph for the chloride as well. Sorry, for the fluorides. So you can then put in the order of stabilities. For example, in oxide, CaO is more stable than E2O3. And CaF2 is one that is quite stable than REF3. But in chlorides, KCl, potassium chloride, sodium chloride, lithium chloride, calcium chloride, they're actually more stable compared to the rare earth chloride. So that's why chloride-based sort of high temperature processing to process these rare elements is more suitable compared to when we're dealing with oxide there. Right, so we talk about molten salt electrolysis. So as I mentioned earlier, in essence, we try to dissolve the different types of compounds, chlorides or fluorides, and oxide as well, into a salt bath, which also made of chlorides and fluoride. So the bath itself, we call it electrolytic bath, and we have the rare earth chloride and fluoride or oxide as the raw materials, and then we also have the cathode, right? We can have consumable cathode, anode, and we can also have non-consumable as well. Right. So the idea is we apply current and voltage across these electrodes. Basically, we form gas. If we use carbon as an anode, we form gas CO2 as the carbon is oxidized. Yeah. So remember, in anode you have an oxidation, and in cathode you have reduction. So this in cathode where we deposit either liquid rare earth or solid rare earth, depending on the time, also the voltage there. So typically, for example, for the ND neodymium electrolysis, we use lithium fluoride, barium fluoride, and calcium fluoride for the bath. The temperature usually about 1030 to 1070 degrees Celsius. We use current about 2200 ampere, voltage of 10. We can use cathode made of molybdenum, and the power consumption rate is about 8.6 kilowatt hour per kilogram. Right. So that's sort of the molten salt electrolysis process to make a neodymium. Right. So the basis of the voltage is, of course, the decomposition voltage of the particular element itself. Yeah. Now this one is showing the summary of the different types of the salts that we use, and also the product that we can get, and also the types of cathode as well. For example, here we can use chloride bath and using chloride rare earth elements to produce a mix of rare earth elements. So mixed metal is all of the rare earth elements in there. You can also use you can also use non-consumable cathodes such as molybdenum and tungsten. You can also use carbon anode and so on. Right. So this, I just want to show you this graph, basically showing the standard decomposition voltage of different compounds, chlorides, oxides, and fluoride, for these different types of rare earth elements. So the basis is as you can see from here, they also quite sort of similar as well. So it is very difficult for us to just targeting a particular voltage, try to deposit or try to condense a particular element because they are so close together, right? Also the problem is when we do molten salt electrolysis, sometimes definitely we will have to put in more voltage because there are many sort of losses as well as resistance that we need to overcome in the bath. So that control is sometimes quite difficult. So that's why sometimes we have a mix elements in the product, deposit in the product, or form in liquid in there. Right. Okay. So right. So that's basically the general processing of rare earth elements from the ores into the compounds, chlorides, fluorides, and oxide, and then also the making of alloy, right, through reduction, metallothermic, as well as molten salt electrolysis, right? So now we can we get some ideas of the process. Now, what I want to explain now is the once we got a product, once we get a magnet, yeah, how we actually process this this magnet, how to recycle it. So first of all, I would like to talk about the stock availability of the end-of-life REPM, rare earth permanent magnet. So of course, mainly the REPM is coming from different application, right? But most of them are coming from electronics goods, e-waste, such as from loudspeakers, mobile phones, as well as hard disk drives, right? So those are the main sources. Yeah? For example, in particular, HDDs, the hard disk drive, we manufactured around 600 million units per year. If you have about 10 to 20 grams of NdFeB in this HDD, in the hard drive, so you'll have about 6,000 to 12,000 tons of NdFeB alloy that can be processed or should be processed. Yeah. Now, the typical concentration of this REPM can be seen here in the table on the right. So there is called sintered body there. So that's basically the magnet itself. And the neodymium concentration is about 23 to 31. We have a bit of praseodymium and dysprosium. So we usually add these elements to improve the magnetic properties on a small amount. But the majority is iron, 60% to 70%. Right? And we also have a bit of boron as well in there. Right? So the main thing here is mainly it's iron. The second one is neodymium. Right? So these are the main sources of EOL REPM. Now, usually when we also process a during manufacturing of magnet, sometimes we do a cutting and also other sort of forming process, right? And that also generates some waste. So we call that grinding sludge, right? And in a sense, the concentration also similar. But what I'm trying to say in here that sludge is also a source of NdFeB. So we don't want to throw that away, and we want to also sort of process that one to get the NdFeB. Okay, so it's already about an hour, so we're still okay with time. Yeah, okay, so let me just continue. Right, so now, but the other thing that we need to be mindful of is the fact that we recently there's a growing sort of use of electric vehicle and need of or demand in electric vehicle, and with time, with the current sort of push around the world through electrification, there's an expected growth rate of electric vehicle use, and basically this magnet also used in electric vehicle, in electric motors, for example. So in addition to that source of hard drive, right, there is also expected increase in the source of EOL and the FEB, EOL REPM from electric vehicle, right? So the one on the right there showing us the expected EV sales, electric vehicle sales. So by let's say 10 years from now, about 2031, for example, we expect about 25 to 30 million vehicles is in the form of electric vehicles around the world. So there's a clear expected growth in there, and with that, it also comes with the NdFeB. So we have about usually 15 years of life of electric vehicles. So so we will expect in the near future, starting 15 years from now, we have quite a strong flux of end of life REPM from electric vehicle. Right? So the one on the left there is showing the magnet itself, and also the where we use it in the electric motor in the electric vehicle. Yeah, so that's a picture from Nissan Leaf. So right. So now let's try to look at how we can process this REPM or end of life REPM. Yeah. So as with in general e-waste, yeah, one of the key problems or key barriers to recycling is whether, well, first of all, is how we actually dismantle and also recover or get the actual physical magnet itself. Yeah. So we can do it by hands manually, and that's really good in terms of separation. But of course, in terms of the cost for labor, that is not good, right? And we don't have currently a clear, a fully automated 100%, machine dismantling process. Yeah. So in a way, it's sort of still a combination of dismantling by hands with some automatic machine assistance, right? So that's one of the main barrier there. So in general, the process follow the following. First, uh, we dismantle them, and then after we dismantle, before we go into any other the next process, we usually demagnetize the magnet because it's still quite dangerous. For example, if we process it directly, it sticks into the blade, or it sticks into the reactor. If you make the reactor from ferrous types, or magnetic sort of material, right? So it can interfere with the processing, physical processing afterwards. So you first demagnetize it. There are two ways you can do it. You can thermally demagnetize the magnet. In a sense, you heat it up above the Curie point, which is about 350 degrees Celsius. And in here, there are advantages and disadvantages. Of course, the advantage is pretty simple. You just heat it up. You can also heat up or process large amount of materials. Yeah? So you can go just put it in the big and then you put it in the furnace at the same time in large volume. Right? There are disadvantages that includes, for example, if you have some components in there that is hydrocarbon, non-magnetic, for example, such as binders, glues, some coatings or plastics. So that's not good because it can sort of create vapor, unwanted sort of hydrocarbon harmful gases, for example. And of course, the fact that there's other elements in there, or the other component, we add more heat into the process, and we also have loss of energy in the process. The second way we do it is through non-thermal method, right? So in here we are using magnetic force applied in the opposite direction, yeah, on the opposite, yeah, in terms of magnetic field, and to sort of nullify the original magnetic field in there. Now, you can do that, but it's generally quite expensive, and it is very difficult. Oh, yeah, because of expensive, and also you need to have quite a large. Sorry, if you want, it's also difficult to treat large amount of waste at the same time because you will need to have quite a large reactor and also strong magnetic field in there. So now to have something like that is quite expensive. Right. Now, in terms of the dismantling after that one, there are different ways, but I mentioned mainly it's by manual, by hands. But there's some sort of semi sort of automatic types of process. For example, here Hitachi use a drum separator, right? So in a way, for example, if you have hard drives, right, you put it in there, it's just tumbling. What happens is it will it will break, or it will remove the caps, or it will break it down into different sort of components in there. But still, in the end, we have to take the particular magnets from there manually, yeah, or using visual screening to identify which one is the magnet. There's also use of non-magnetic knife, non-magnetic threader knife, right? So in here, it's sort of semi-automatic as well. So you try to expose the magnet as much as possible, and then use sensors, which is also from magnet, to identify which one, which part of the component is the actual magnet. Yeah. Because if you look at hard drive, you can see there are many components in there, and the magnet itself is sort of concealed inside in there. So this sort of a semi-automatic process can process 100 to 200 hard drives per hour. Yeah. So it's not bad, but still it's not a fully automatic. There is some sort of manual process involved in there. Once we get the magnet itself, we can use different types of process, right? So remember previously, the first thing that we do when we process the ore from the ore is we produce oxide, chlorides, and fluorides, right? So that also can be the route that we use for recycling of REPM, right? So in here, I want to focus on the pyrometallurgical aspect, right? Because there's also hydrometallurgical aspect of processing of REPM, but I want to focus on the pyrometallurgical aspect in here. So you can take the oxidation route, right? You can take a chlorination route to form chlorides and oxide, right? And you can use hydrogen. You can put it back directly into electrolysis, molten salt, and you can have other methods such as liquid metal extraction, distillation, and other technique in there. Now it comes down to what do we want to do, right? We want to get do we want to reuse the magnet and sort of to remanufacture as a new NdFeB magnet, or do we want to recycle them back? Do we want to recover the neodymium, right? Or do we want to produce the semi products such as oxides, chlorides, or fluorides? Yeah? So that will govern the choice of the process in there. Now, this one is just to give a snapshot of comparison. So this is quite crude, but it gives some idea in a way of the different recycling route in terms of what temperature we operate and what processing time we use for the recycling process. So we in here, and this is also coming from one of our paper, which is on the review of recycling of REPM from high temperature process. The one that I showed earlier at the beginning of the presentation. So in here we classified through chlorination, like the blue dot. Oxidation is a purple. For example, here the red one's electrolysis. The green one is pyrolysis, right? So as you can see from here, for example, the oxidation, it tends to have quite a significant time, right? Because later I will also show that result, an example of that process. But also it takes a high temperature as well to produce these oxides. For example, 0.2, this one is, and 0.3, this one actually beyond the melting point. So we actually melt the NdFeB, and we form sort of oxides of these rare earth elements in terms of rare earth oxide mixed with other elements in there. These are showing a summary of the different processes in terms of the process conditions, the source materials, the types of reaction, whether it's gas solid, liquid solid, liquid liquid, the typical experimental conditions, and the reagents that we use to form the rare earth products, right? So for example, the green one on the top is where we want to produce either oxides and chlorides. And in here, I'll just take an example. We can take an example of 0.3. So we have a solid scrap, and we can take a selective extraction and vacuum distillation by using magnesium chloride. So in a sense, we reacting the chloride with the neodymium to form quite pure neodymium chloride. So so that's an example, and there are also other types in here. Number 7, for example, because I've got a picture later on. So number 7 is when you you have the solid scrap, so you have the magnet, right? And then you first you melt it up to 1650K, and you add boron oxide to form a slag. So in the end, you get this mixture of Nd2O3 and B2O3 in the slag, and you can then separate the Nd2O3 from B2O3 by leaching using using particular chemicals, so just to remove the boron oxide. Now I won't go through the details in here as well. So this is also a summary of advantages and disadvantages of different pyrometallurgical recycling routes, right? Ranging from, while you're using whether it has a long reaction time, higher temperature, and so on. Again, this is coming from one of our papers. So the details of this can be looked at in the paper. I probably can send that around as well later on as part of the. I also will give a copy of this already to Ibu Winnie, and I can also give some paper or two as well to add to your reference. This is the thing that I mentioned earlier. So in here, we use boron oxide, basically, to make some slag, right? From the NdFeB. So in here, we have NdFeB magnet waste. So you already sort of make it into small pieces in there. You crush it, right? And then you put it in a remelting furnace. This can be electric arc furnace or other types of furnace, yeah? And then you mix it with boron oxide as a flux, right? So now remember, as you see the Ellingham diagram or the graph that I mentioned earlier. So when you do this, what happened is all the rare earth will form an oxide, and then we form a slag. And we add that with B2O3 or F2O3. So you form a Re2O3 B2O3 slag, right? And the iron and the Fe2B will form in the metal, right? So you separate them, the metal, which is mainly iron and Fe2B, and you get the slag, which is mainly the Re oxide plus the flux. Yeah. Now the slag itself can be then leach, right? So and the B2O3 will be removed, and you'll end up with quite pure or quite highly quite high purity slag. Sorry, oxide here. Right. So this one here, an example of quite a complex process here, but the idea here is we use we try to make chloride. In here we react NdFeB, right, with aluminum chloride, and then in essence we or chlorine basically, right? In essence we form this neodymium chloride, right? And you can use different processes such as either solid liquid separation, either vacuum distillation, or CVT transport. And the choice here will give us the different types of products that we can get from the from that. Now again in here, you can see the choice is yours, and depending on the availability of the furnace, for example, or the reactants. Another interesting process is using liquid magnesium as a way to extract neodymium from the magnet, right? So this is quite interesting process. It's developed by Takeda and Okabe. So in essence, it takes advantage of the high pressure or high vapor pressure of magnesium, right? So it's about 0.73 atmosphere at 1300 K, but also the fact that the vapor pressure of neodymium is quite low, which is about 10 to the minus 6 at 1300 K, right? So the process is shown on the right. You, in essence, have a magnesium, liquid magnesium initially, right? So we take it up to 1300 Kelvin, and basically we make magnesium vapor, and then it goes to sort of the top here. There's a condenser where we deposit this gas, right? But when it touches the condenser, which is operated at lower temperature, it becomes liquid, and the liquid drip into the scrap chips. That's the blue one or the purple one there, right? So as the magnesium liquid pass through these chips, right, it sort of absorb the neodymium, right, and then and trickle down to the crucible at the bottom, right, and then you form this magnesium neodymium alloy liquid. Sorry, yeah, liquid alloy, and the process keeps continuing. It keeps recirculating. So basically, more and more neodymium getting extracted from the scrap chips. You'll end up with just the Fe and the boron particles, right? And more the neodymium concentrated in the magnesium liquid at the bottom there, right? So once everything finishes, most of or almost all the neodymium goes into the bottom. Then you can separate the magnesium by, for example, vacuum distillation, right? And you can get quite a nice high purity up to 97.7% neodymium from this process. So in here, there are, of course, advantages and disadvantages. So the advantage, for example, in here, the liquid metal solvent in theory can be recycled and reused and again and again, right? As long as you don't have leakage, right? There's no magnesium gas going out, for example. And in here also the waste streams are kept to a minimum, right? There's no other sort of remain other than, of course, the FEB, but that also can be processed as well. Now the problem is if you have oxides, yeah, then the magnesium cannot really penetrate through and react with the neodymium. So it cannot be used for when you oxidizing when you have a REPM that is heavily oxidized. Yeah, and the process also is relatively slow. Now in here, of course, the fact that the process is quite slow means that we need to provide the heating in a long time. So, regular heating will be quite high. Right, there's also a process called hydrogenation, right? So in essence, hydrogenation is you try to react the hydrogen with the NdFeB, with the magnet, right? So this sort of in line with the what is called the HDDR route. So I didn't put it in here. So when you manufacture the magnet in the first place, there's a process called HDDR. It's called hydrogen decrepitation, hydrogenation, disproportionation, desorption, recombination, right? So the idea is you in the original process when you manufacture magnet, yeah, so you can actually melt NdFeB, right? So you have a particular composition of NdFeB and then you melt them and then you cast them, right? Once you have a cast NdFeB mixture in the process, you react it with hydrogen at high temperature, and what happens is the hydrogen will be reacting with the neodymium, forming hydride. Right? Now this is quite a exothermic reaction, and also there is it's accompanied by 5% volume expansion. Right? So what happens is when it reacts, it actually actually crumble because there's enough volume expansion. It becomes powder, and in the end you have this NDH2. You have Fe and Fe2B mixture powder, right? Now in the original manufacturing process, you can then form that. And then you sinter that to make the final NdFeB. You can use a direct sintering. Also, you can use you can mix with something first. Oh, forget what it's called. Resin. It's also you can directly sinter it, or you can also resin bonded the magnet. So you add a resin. You still need to heat it up, of course, but in the resin bonded magnets, you use this chemical to consolidate to form a shape of magnet and then heat it up. But when you can also directly sinter it, which is just you press it and then you sinter it. Yeah. So the advantages of this is okay. So hydrogenation means that we use this kind of approach to react with the NdFeB magnet. Right? So the same phenomenon is happening. You sort of undergo hydrogen decapitation, so the magnet will be crumbled, right? and then after that you can sinter it again. So the advantage is this is you can reuse of REPM. So you process end of life REPM to make a new REPM, right? So but the second REPM, the recycled REPM usually has a lower life cycle. The life is shorter. Of course, uh, in here, we cannot use it to recover the rare earth. We just reuse it to make REPM, right? Um, and um, and there is a, it has been reported that the efficiency of the separation can be about 95%, right? So which is pretty good. One of the disadvantages is there's a reduction in the magnetic properties, so it's not really as good as the original, for example. And the same thing in here, you cannot really use REPM that is heavily oxidized. Yeah. So the one on the bottom there is process conditions that we use for this process. In essence, first we put it under vacuum and then we heat it up to a particular point. So usually it's 1153 Kelvin, quite a high temperature. And then we bleed that with hydrogen. So you use hydrogen pressure in there. And as you introduce the hydrogen into the reactor, then the reactions happen. So this proportion reactions and formation of hydride. And then of course, and then you do recombination by lowering the pressure as well, and also the temperature. Right. Now, there is the next few slides. Now, I'm conscious of time, but the next few slides, which are still many, but I'm going to do it quite fast way. I just want to explain the idea that we have. So in Swinburne, we try to develop this process. In essence, we use solar energy, right, as a source of heat to oxidize rare earth permanent magnet, right, with the aim to form NdFeO3, or we call it REEFeO3, right? And we separate the neodymium or the rare earth element as REEFeO3, right? So we recover it as NdFeO3. So first, we use solar energy to reduce the energy consumption because we found that the process, it takes 24 hours at least. Right? And we then use so the idea is we use rotary hearth furnace with concentrated solar energy to oxidize the magnet. And then we use a series of physical processing that combine density separation and magnetic separation to separate NdFeO3 from this magnet. Yeah. So in here we don't need to have other chemicals and it's just a concept that we develop and we're currently developing this and fine tune the process. So why we want to recover the REE as REEFeO3? So this is why. So REEFeO3, such as NdFeO3, is a magnetoelectric materials, right? So it is a material where we can turn on and off the magnetic properties just by applying current to it. So currently, people in materials physics is focusing on these types of materials to develop a new generations of magnet, so a new generation of NdFe, permanent magnet. Right? So this is we call these types of material also magnetoelectric or multiferric materials. Right? And the application is like magnetic materials, It's used for data storage, gas sensors, absorption, and also other gas detection. So the rare earth orthoferrites is actually a perovskite type structure shown on the right there, and you can have different types of rare earth elements substituting this octahedral. Is it octahedral? Yeah, in that position, the green position basically. Yeah. So it can have lanthanum, praseodymium, neodymium, samarium, and so on. So that's the idea. So the reason I just want to show you microstructurally what happened when we oxidize the magnet. Yeah. So this is a high temperature XRD that we did when we heat it up. We heat up the magnet. So the main phase of the magnet is Nd2Fe14b, right? So when we heat it, when we heat it up um, in helium, so this picture is the XRD. So the one on the left there, we heat it up from 298 to 1373 in helium, right? So so as we heat it up, then as you can see in here, you started to produce alpha iron, right? And then Nd2O3 as well as NdBO3, and at higher temperature, we also start to form gamma iron. Now the three-dimensional representation of this can be seen on the right-hand side. So basically, when you heat up the Nd2Fe14b, which is the main phase in the NdFeB magnet, it will thermal dissociate into alpha iron plus Nd2O3 plus a bit of NdBO2O3. Right? But if we heat it up in air, then immediately we also started to form NdFeO3. Right? This can be seen in this graph here. So the one on the top here from 1373 is when we switch on the XRD from helium to air, we started immediately to form that oxide in there. So we did quite a systematic study on this one. So we oxidize new uncoated REPM. And we found that if we oxidize it at different temperature, it will give us different types of microstructure. So don't worry about this sort of complex schematic, but in essence, when you oxidize it, let's say in here is from 1000 to 1300, you will form quite a thick layer of Fe2O3 on the surface. We call that in the EOZ here, external oxidation zone, mainly consists of Fe2O3. And then we have an intermediate layer where we have interspersed of FeO, Fe2O3, Fe2O3, and NdFeO3. We have IOZ, where we have iron as well. So this one here is basically a product of the thermal decomposition as we heat it up before, right? But in here, we have only small amount of oxygen or no oxygen yet. So it's just thermal decomposition. But as oxygen passed through, it forms this intermediate layer where we started to oxidize the iron into different types of iron oxide. And of course, on the core, we have this unoxidized NdFeB net. Heat it up at higher temperature, which is 1300 to 1500. The layer one here, we started to form quite a nice NdFeO3 phases, which is segregated in this layer in the form of lamellar structure with Fe2O3. So this is the basis of our ideas. In essence, I have a picture next one. Oh yeah, this one. So this is pretty good. So this is oxidation at quite high temperature. So what happened is, as you oxidize, you started to form a thick layer of Fe2O3 on the surface, which is the gray one, external oxidation zone. Now the gray one is quite easy to remove, because when you just slight tap of the surface, you can take it off easily. And then we have a layer one where you mainly have a concentrated NdFeO3. That's the one, that's the phases that we want to extract, right? Interspersed with Fe2O3, right? So, and at the center we have this magnet core where it's not sort of oxidized. So the idea is we do oxidation, right? And then we remove the outer layer, and then we can continue the oxidation until fully separation of Fe2O3 can occur, and you have this you'll end up with this layer of NdFeO3 rich, right? We still have some iron oxide in there, but with after crushing and physical processing, the aim is to separate the NdFeO3 from there. Yeah. So that's the central idea that we use for the process that we are proposing there. Now, so this one was studied by a PhD of Firdaus, right? So, so in here, he was focusing on new uncoated REPM, right? But the question arises, what if we have this end of life REPM, right? What happens if we oxidize it? So currently, Dedi, one of my students, is focusing on studying that, right? So in here we have the magnet. The one on the right is the magnet I mentioned. In practice, the magnet, the actual magnet, has a thin layer of coating on the surface, right? So it can be nickel, copper, nickel, such as shown in here, and it can be other metal coating. The purpose of the coating is to improve the corrosion resistance of the magnets, especially high temperature corrosion. Yeah, when it gets hot, so that it's not oxidized and it's not sort of breaking down. So that's the purpose of the coating. Now, so as you can see, the coating is pretty thick. That's about, I guess it's 10 micron, I believe. Yeah, it's about 10 micron. Now, this one is the magnet, end-of-life magnet that we use, coming from Not Printing Australia. So it's coming from machine to print money, right? So to print money, there's a printing machine, and it uses a permanent magnet in the process. So this is the one coming from them, but it's basically similar to the composition of, for example, the one that used in electric vehicle and so on. So we do oxidation study and also do some kinetics analysis. I won't go into the detail, but that's just want to mention in there. So, and then we study the microstructure, right? What we found that is when we have some coatings, it has a strong effect, first of all, on the microstructure evolution, as well as on the kinetic itself. Yeah. So at different temperature, we also find different microstructure evolution, right? And the nickel oxide coating actually stays in there, sometimes also forming a mixture of nickel oxide and copper oxide, and it actually hindered the oxidation quite significantly. The other thing that we found is that when we have this coating, the structure of the NdFeO3 is slightly different compared to the one that we have before, right? In the case of new and uncoated magnet. So for example, on the right here, if we oxidize at 1373 and 1473, instead of have a lamellar layer, like a strip layer of NdFO3 and FeO3, we have quite a blocky or sort of clumpy NdFO3 faces here, right? So the one shown on the right, where you have this blue um, faces in there. So that's in a sense good, because it may be easier to have something like this, and then when you have quite a thin layer of lamellar structure, when we want to separate these blue faces. Yeah. So yeah, so that's something that we analyze, or we observe. Then we also try to develop the mechanisms, or I won't go into the details of this one. In a sense, at different temperature, we categorize into four. We found 4 category of microstructure, right? The one category 1, 2, and 3, and 4. And it has a different microstructure evolution as well as the microstructure at the end. Yeah. So we also analyzed the kinetic, and we found that we can fit this into a Kinsling-Braunstein model, right? Common model for solid gas reaction in there. And we found that the energy activation is about 168 kilojoule per mole. And this one actually similar to oxygen diffusion energy activation for oxygen diffusion in copper oxide, oxygen diffusion in nickel oxide, and oxygen diffusion in gamma Fe, right? Roughly in that sort of region. So considering the microstructure form, we sort of deduce that the rate limiting step in this oxidation is in a sense diffusion, right? And we think that, for example, at 1973, the rate limiting step is oxygen diffusion in the mixed layer of nickel oxide and copper oxide layer. Thus, the effect of coating is quite significant in here. At 1073, we still thought that this this layer also affecting the process, and it's controlled by oxygen diffusion through this coating layer. Now, what's interesting is when we heat it up at high temperature, say in 1373, we did not see any nickel oxide layer anymore. So the nickel oxide and copper oxide actually diffuse inwards, so and dissolve, forming a mixed oxide, right, with neodymium and also FeO3. So we thought that at this condition, at very high temperature, the process is limited by oxygen diffusion through gamma Fe, which is similar to the case when you oxidize new uncoated magnet, as I showed you earlier. Right. So this actually summarizes the kinetic study that we did. So I just want to point out on the left hand side in here. So the this diamond black data, symbols, basically coming from the work for the end of life oxidation. The one, the open circle data is the new one. Now, as you can see, at temperature from 973 to, let's say, about 1273, let's say, yeah, 1173, the rate is actually lower compared to oxidation rate of new uncoated magnet, right? So the effect of coating in there is quite significant. However, if we heat it up or oxidize above 1273, the kinetics is the same, right? So it doesn't really matter. So that what give us sort of some sort of we can summarize and the implication of this coating to the recycling process. So so basically we should remove this layer first if we want to effectively oxidize the magnet, especially at low temperature. But if you want to do it at higher temperature, then it's okay. It's the same. However, we don't know the effect of nickel and copper on the NdFeO3 yet, whether that's a good effect or bad effect. But definitely some of the nickels and basically nickels come into the REFeO3. So we don't know whether that's good or not. Right, so just to summarize, basically there are a number of techniques to recycle end-of-life NdFeB, right? Most of them were demonstrated on laboratory scale, right? And no major industrial or continuous process currently work applied commercially for recycling end-of-life NdFeB. So the chance still there. So you can be part of that solution to develop a process there. And we also try to develop our own sort of process with the aim of recovering neodymium and other rare earth elements in the form of ReFeO3, multiferric materials that's quite useful. But in here, we want to use concentrated solar energy to make sure that the energy requirement is okay, right? Because you need to oxidize this for about 24 hours. And also we did oxidation studies in the lab showing that the coating in end-of-life NdFeB affect the oxidation process and the kinetics. So it is advisable to remove this coating layer to obtain quite a highly separated NdFeO3. So that's basically, this is other sort of references that can also be read that relates to this presentation as well. Right, so that's basically my presentation. So we still have time, that's good. And we can have a discussion or comments or other things there.
Okay, thank you, Professor Akbar. And the students may find very lengthy lecture, but I think that's very important as well. So you can see the students can see the structure of the work, yeah, from the very general, the ideas, and also go to the laboratory work that will have a big impact on the later for recycling rare earth. Okay, do you if you want to have any question, please raise hand. Okay, Ahmad Atoilah, do you want to put it in the chat or do you want to talk by yourself? Okay, I will read it. Yeah, sir, I want to ask, what do you think about e-waste management in Indonesia? Is it possible to do urban waste recycle to some REE with the current condition in Indonesia e-waste management, or do you have suggestion how Indonesia should do to maximize this potential of urban waste?
Thank you very much, Ahmad. So that's a very important question. There are a number of challenges that we have currently in Indonesia, but I believe that in the near future, we should be able to address this one. First of all, currently, we just have got a new legislation about e-waste. So in 2020, so we had two before, but it's not clear, but focusing on industry. But currently in 2020, there's one that also focusing e-waste classified e-waste from household as well, right? So at least first of all, there's a progress in the legislation. Second is we don't have quite a a formal recycling, formal collection system in Indonesia yet, right? So there is a limited and sporadic sort of collection process, usually through informal process such as scavenging. You know, people go door to door and collecting e-waste and then put that into a particular sort of location. So if we can have a national sort of scheme for collecting e-waste, that would be good, right? So I should mention there are already some of them in Indonesia. For example, in Jakarta, I believe there is already one through, for example, Council, right? But if you have a national collection, a scheme, that will be very good. Third one, we don't have quite a good management in terms of, okay, once it's collected, who's going to process this one? Now, currently, I believe the process is also informal. So you do it in the backyard or something like that. Or the one that formal is actually you send it to other countries. So in a couple of months ago, I delivered this sort of presentation about e-waste processing, and at the same time, there's a person from industry. I think the company called TES. So they collect e-waste in Indonesia, but they don't process it in Indonesia. So once they collect, they just send it to, still in their company, but they process it elsewhere. But what it means is the value is taken elsewhere, right? So we still don't have quite a nice system in there. So overall, the systems need to be developed, the recycling system. So in the work that I've been doing right now, I try to propose an idea of having a recycling system where we integrate this informal collection through scavengers with mini substation e-waste processing facilities, combined with or integrated with the large smelters in Indonesia, right? So so that can be done, right? So and I'll actually now 2 days from now I will be I will be discussing with a number of ministries on trying to develop a circular economy strategy in Indonesia, particularly on e-waste. So I believe the opportunity is high, right? And you currently, as an engineer, in a year or two, and once you finish, hopefully you can apply your learning in pyrometallurgy or process metallurgy to contribute to this problem. So it's quite a complex problem, but I think Indonesia can play a big role in here, because the amount of e-waste in Indonesia is pretty high within Asia, and the total e-waste in Asia compared to the world also pretty high as well. So if we tackle it in Indonesia, then we contribute to the solution of the global problem. But at the same time, Indonesia also can get the benefit from processing these e-waste.
Okay, thank you for the answer, Professor Akbar. Any other questions, please?
You can ask anything. You can ask, for example, how's the studying in Australia?
Melbourne now has
Or
the
if you
state of COVID, yeah, so everything back to normal, yeah.
Oh, it's not, well, it's still not back to normal 100%, but in Melbourne, for the past more than 3 weeks, for the past 3 weeks, we don't have any new COVID, cases. So there's another outbreak in South Australia, but in Victoria, we sort of okay. So hopefully it's going to be in the new normal soon, but it's pretty slow. Yeah.
Okay, one last question. Okay, if there's no question, I would like to ask questions. Yeah, what do you think
Sure.
about about the processing of monazite in the tin tailing, because it has the radioactive material, yeah, thorium on the
Yes.
monazite. So which one is bigger? Is it the economical consideration or the environmental? Which one has a very bad, good or bad impact? Which one is bigger?
Yeah. So actually, that's a good question, because one of the drawback is the fact that when we process this monazite coming from the heavy minerals mainly, we have this thorium and also uranium, a bit of uranium as well, and to process them is quite expensive if we want to separate that one. So uh, well, so to answer that question, is both economically not good, but also there's also a hazardous sort of aspect to the process. But people process it, um, uh, so I guess you have to look at the bigger picture, whether the whole process overall economically viable or not. If maybe my suggestion is, if you only want to process the monazite only, economically is worse compared to, let's say, if you look at a bigger picture where you process everything, you also process the ilmenite uh, um, and get the value from that, because majority of the ores itself is not the REE ores, but it's the mineral sand itself, the rutile and the ilmenite. So if we are able to process that one, generate or produce rutile or ilmenite or even titanium. At the same time, we also incorporate the processing of REE. Overall, it will be more economic. So that's sort of my view on that.
All right. Okay. Thank you very much, Professor Akbar. So I think looks like it is very interesting, and also the homework for us, yeah, in Indonesia, to how we meet the demand of rare earths in the future. Is it from recycling or is it from monazite processing? But anyway. Okay, and I would like to give a certificate of appreciation from the chair of chemical engineering, yeah, Pak Arse. I think you know Pak Arse as well. And thank you very much for having share your time with us to talk about your work. Okay, everyone, and then looks like this is the end of the our uh, our lecture, and thank you very much for listening. And then okay, and we'll see you again for the students tomorrow, yeah, at 3 o'clock, and we'll continue about electrometallurgy. Okay, so we have 1 week left of the 1 week left of the lecture, and
Okay.
everybody's happy. So anyway, okay, thank you very much for listening. Thank you, Professor Akbar. And
So
okay, before we go,
when is the
yeah.
no, I want to ask, when is the final exam? Is it
Oh yeah,
in
yeah.
December, or is it after
December.
the December? Okay. So I
Before we
just
go,
wish
yeah.
you.
Yeah, I would like to take pictures. So can you open your videos, and I will take picture for you as well. Oke, siswa, silahkan dibuka videonya. Mungkin disisir dulu, langsung. Oke. Ya. Oke, semoga tidak tidur semua ya. Oke. Ya. Oke, so bentar, masih sedikit. Ya, oke, 1, 2, 3. Satu lagi. 1, 2, 3. Okay. Thank you for listening, and then see you. Thank you, Professor Akbar, and then see you tomorrow. Okay, bye-bye.
Thank you very much, everybody. Bye.
Bye.